Okay, let's dive right into this explainer. Today, we're decoding the foundational language of mathematics, and it all starts with mastering the concept of sets. Look, whether you're charting complex data, writing algorithms, or honestly just trying to organize the chaos of the real world into neat, logical boxes, understanding sets is absolutely your crucial first step. We're going to break this down visually, so it's not just a bunch of dry formulas on a page. No, we're building a system that actually makes sense.
Here's our roadmap for today. We'll start with the basic language of sets, then move on to categorizing their different flavors. After that, we'll dive into subsets and intervals, explore how sets interact through operations, and finally wrap the whole thing up by mastering De Morgan's law.
All right, part one, let's get fluent in the language of sets. Now, take a look at the statement on screen, a collection of the 10 most talented writers. Now, is that a mathematically defined set? Actually, no. It's totally subjective, right? You probably have your top 10, I've definitely got mine, and chances are our lists aren't going to completely match. In everyday conversation, sure, you can call it a collection. But in mathematics, well, ambiguity is the absolute enemy. So what exactly is a set? Think of it like an exclusive VIP club with strict, totally objective rules for entry. There is zero room for opinion here. If you can't state with literally 100% certainty whether an object belongs, then it's just not a mathematically well-defined set. And this brings us to our VIP bouncer. That curved little E symbol you see there, that's epsilon. In mathematical shorthand, it acts as the ultimate authority. Say we have a set A containing the numbers 1 through 6. We use epsilon to declare unquestionable membership. Does the number 5 belong to set A? Yup, the bouncer lets it right in. Does the number 8 belong? No way. So we just put a line through the epsilon to clearly state entry denied. When we're writing in this new language, we essentially use two distinct dialects. First up is the roster form. It's incredibly straightforward. You literally just list out the guests inside curly brackets, separated by commas. It's your physical guest list. The second dialect is the set builder form. This one doesn't list the guests at all. Instead, it dictates the exact entry requirements. You're basically saying X such that X meets this one specific condition. What makes these two forms so great is their sheer flexibility. Whether we're solving for the roots of a quadratic equation on the left or mapping out a complex sequential pattern of fractions on the right, we can translate these big ideas perfectly into our set formats. You just identify the core relationship, like noticing the denominator is always exactly one more than the numerator, and you capture it elegantly right there in set builder notation. Moving right along to part two, let's categorize our sets. Okay, the concept of the null or empty set is honestly pretty fascinating. It perfectly describes mathematically impossible scenarios. Take a look at this first example, finding an odd natural number that is perfectly divisible by 2. By definition, that literally cannot exist, so the set of those numbers is completely empty. It is the mathematical equivalent of an empty room. Sets also need boundaries. We have to ask ourselves, are we dealing with a bounded reality, meaning a strictly finite set you could theoretically count up, like, say, all the animals currently on Earth? Or are we dealing with an infinitely expansive one that stretches forever without an endpoint, kind of like parallel lines? Recognizing that distinction right off the bat entirely changes how you approach a problem. And then, we have the ultimate test for equality. For us to declare two sets completely, mathematically equal, every single element must match perfectly. Now, the order they're listed in doesn't matter one bit, but the roster itself must be identical. Look at the second example here. Set A is multiples of 10, but set B lists 10, 15, 20. See that? Because one rogue number, that 15, slipped in, the equality is permanently broken. They are simply not equal. All right, let's dive into part 3, subsets, powers, and intervals. So a subset is exactly what it sounds like. It's simply a smaller, fully contained group that's been extracted directly from your main set's population. It's like little boxes inside a larger box. If your main set is just the letters A and B, you can break that down. You get a set containing just A set containing just B, the set containing both, and, this is absolutely crucial, the empty set. The empty set is fundamentally a subset of every single set imaginable. Now, what if you need to quickly calculate exactly how many possible subsets you can extract from a master list? Well, good news, you don't need to write them all out. You just use this incredibly powerful exponential formula, 2 to the power of n. And n is simply the number of original elements in your set. So if you have 3 elements, it's 2 to the power of 3, meaning you have exactly 8 possible subsets. The collection of all these subsets together, we call that the power set. But wait, what if our set isn't just a discrete list of distinct integers, but an infinite, continuous stretch of real numbers? Well, for that, we use intervals. Look closely at the notation here. It's super important. We rely on square brackets to explicitly include the boundary number and round brackets to exclude it. So a round bracket next to -3 means we start just after -3. But a square bracket next to 0, that means we stop precisely on the 0 and strictly include it in our set.
Onward to part 4. Let's talk about operations on sets. This is where things get really fun. Consider this your ultimate cheat sheet for basic operations. Think of the union, represented by that big U symbol, as a giant, highly inclusive gathering. It merges populations completely. If you're in set A or set B, you are invited to the union. Intersection, on the other hand, represented by the upside-down U, acts like a really strict filter. It catches only what both sets have exactly in common. You got to be on both guest lists to make it through an intersection.
But sometimes, those conversations between sets just yield pure silence. If we run an intersection filter between set A and set B, and it comes up completely empty, giving us our old friend the null set, we definitively call those two groups disjoint. They're operating in totally different worlds with absolutely zero overlap. You can also literally mathematically subtract one set from another. If we calculate x minus y, we start with the entire population of set x, and then we just peel away any members that also happen to belong to set y. What you're left with is a totally unique, unshared remainder. It's essentially the mathematical equivalent of asking, who is in group X but absolutely refuses to associate with group Y? And finally, for operations, we have the complement, which is marked by that little apostrophe. If you want to look at everyone who didn't make the cut for set A, you find its complement. This simply means taking every single element that exists in your broader, universal universe of data and keeping only the ones that are explicitly outside your specific set. It's kind of like the shadow cast by your set. Which brings us to our grand finale, part 5, Mastering De Morgan's Law. Okay, we are going to verify a genuinely profound mathematical truth here. It might look a little intimidating at first glance, but with our structured approach, I promise it's a breeze. We're going to calculate the left-hand side by first uniting sets A and B, then finding the overall complement of that union. Then, very methodically, we'll tackle the right-hand side, finding the individual complements of A and B first, and then filtering them through an intersection. And as you can see, by plugging our actual numbers into the formula, we beautifully prove the core tenet of De Morgan's Law. Just look at the balance here. We've systematically shown that the complement of a union, basically everything outside the combined megagroup, is perfectly, element for element, equal to the intersection of their individual complements. The logic is just flawless, and honestly, it perfectly bridges together literally every concept we've covered today. So, now that you're totally fluent in the formal language of sets, I want you to try applying this to the real world. Look around the room you're in right now. If you were to create a strictly defined, mathematically unambiguous set of your absolute favorite objects, what would be the objective rules for entry? What exactly is the set builder notation for the VIP club of your own life? Think about that, and I'll catch you in the next explainer.